Fala galera, sejam todos bem-vindos. Hi folks! Nós hoje estamos aqui para começar mais um dia de Congresso Internacional de Astrobiologia e hoje vamos receber um convidado super especial, que é o professor Lawrence Krauss. O professor Lawrence Krauss, ele é um físico norte-americano, ele foi ex-titular da cadeira física de Case Western Reserve Universe nos Estados Unidos, ficou famoso ao sugerir que a chave para entender o surgimento do universo é um tipo de matéria impossível de detectar da Terra, conhecida como matéria escura. Ele também já escreveu diversos livros durante a sua carreira acadêmica e hoje vai falar um pouquinho sobre a odisseia de um desses átomos que compõem a vida pelo universo. Então, deixa eu trazê-lo para junto de nós. Junto conosco também está a professora Glaucia, que vai fazer a tradução das perguntas e também dar uma ideia geral das respostas que o professor Lawrence Krauss fizer ao longo dessa transmissão. E a gente vai estar colocando também aqui o contato da professora Glaucia, professora de inglês, para quem quiser aprender a falar inglês igual a Glaucia e poder se comunicar com o professor Lawrence Krauss, tão bem como ela, melhor do que eu. Então, entre em contato, que ela é professora de inglês e está dando aulas de inglês durante não só essa época de pandemia, mas durante pós-pandemia também. So, we can start, and thank you for coming and give your information, your knowledge for us, Lawrence Krauss. You can start when you want.
Hello? Okay, good. I was hearing lots of echoes, but now I'm not. So, hello everyone, if there's anyone watching, and I hope there is. It's nice to be with you virtually. It's wonderful to be almost in Brazil, a country I have visited many times and loved. And I wish that I was speaking in Portuguese right now. I tweeted about the talk, and someone just pointed out that Richard Feynman gave his lecture in Portuguese, and I remember that, which is why I tried to learn Portuguese, but I wasn't able to. In any case, hopefully you can see me and my screen, which is more important than me right now. And uh, I hope that this poem has been up while I've been talking. It's from one of my favorite poets, happens to be Octavio Paz, and it's well, you can read it. I'm not going to read it to you now, but it's appropriate for the talk I'm about to give. This is a Congress on Astrobiology and Life, and it was really thinking about life that got me thinking about the subject I want to talk about, which was the subject of one of my books. I was at one of my favorite museums in the world, which is the Rodin Museum in Paris, and I was walking around. I love the fact that in Rodin, the thing about his sculptures is that the beautiful images, the beautiful sculptures come out of nothing. They come out of rock, essentially. And I've always been mesmerized by that. But I was looking at this famous image of called The Kiss. And I was thinking about the fact that, well, in a sense, that this is there almost eternally, but it's not there eternally. I was thinking about how ephemeral life is, and love is, and all the rest of the human trials and tribulations, and how one day it'll all be gone from the earth, but what will survive? Well, and I thought maybe these images will, but they won't either. And then I realized that the closest thing that comes to immortality is not life, which is, of course, the question of how long life exists on any planet is a very important open question for astrobiology, and we don't know the answer. But one of the things we do know is that while we will probably not be here forever, by we I mean our species or even our planet, and life on Earth may end, what really has been around a lot longer and will remain a lot longer is the atoms that make up us. So what I want to talk about today is a life history of an atom. An atom in this glass of, this is juice, but there's lots of water in it. that I'm drinking right now. So I want to talk about life history of that atom in that water. When I was younger, my mother told me that when I was drinking something that picked up a bottle she said, "You don't touch that. You don't know where it's been." She would have really been surprised where the atoms in the water that I'm drinking right now have come from, and I want to talk about that. Now, since this is also a Congress of Astrobiology, I thought it would be appropriate to talk about someone who's incredibly important for astrobiology because he's incredibly important for biology, Charles Darwin. Obviously, natural selection is the method by which the diversity of life on Earth arose, and it's undoubtedly, if life exists elsewhere in the universe, it's undoubtedly the mechanism by which the diversity of life will arise on any system. But interestingly, in a letter he wrote to a friend in 1863, he said, "It's mere rubbish thinking at present of the origin of life. One might as well think of the origin of matter." And in fact, at the time in 1863, it was rubbish to think of the origin of matter because we didn't know the laws of physics. But now we do, and it's a subject of great interest. Now, to point out, when we think about the atoms that make us up and the atoms that make up the oxygen atom in that water that I just drank, at the beginning of the universe, there were no atoms or Eves, as it turns out. There was nothing. There weren't any atoms. In fact, it was a hot, dense soup of elementary particles. And one of the biggest questions in cosmology that's been around for about 40 years, really was first discussed by a number of people. I remember I first heard it discussed by the late Steven Weinberg, who was a teacher of mine and recently died, Nobel Prize-winning physicist. And the question is, why do we live in a universe of matter? This is one of the most urgent fundamental questions in science, after all. Now, most people don't think of this question when they wake up in the morning, but the point is that we now know that that elementary particles all have antiparticles. So there's matter and there's antimatter. And antimatter, one of the properties of antimatter is that it has the same mass, opposite electric charge, basically the same properties as matter. And in the hot, dense universe, if you were creating a universe early on and filling it up with particles, you'd fill it up with equal amounts of matter and antimatter, because really if you have a certain amount of energy and you can create particles, you'll create as many antiparticles as particles because they have the same mass. But that would be a big problem. If the universe had equal amounts of matter and antimatter, we wouldn't be here. I wouldn't be here to be giving this lecture, and those of you who are still listening wouldn't be here to listen to this lecture. And the reason is that matter and antimatter annihilate. And if there were equal amounts of matter and antimatter in the universe, then early on in the history of the universe, all the particles of matter would have annihilated with all the particles of antimatter, and there'd be nothing left but radiation. And clearly that's not the universe we live in. So the question is, how did we start, presumably from a universe which had equal amounts of matter and antimatter, to a universe that ends up today just having matter? And that's a central question in cosmology that we've been dealing with. And the answer may be discovered with this image here. Underneath these are the mountains. When I ask people where these are, people come up with all these different answers. But these are the Japanese Alps. This is the image that you might have seen as the Mongol hordes were invading Japan in 1281. But underneath those mountains in the Japanese Alps is a physics experiment. And it's a very important physics experiment. Deep under those mountains, in a working mine, is a tank with 50,000 gallons of 50,000 tons, I should say, of not gallons, 50,000 tons of pure water, purified to remove all radioactive contaminants, put in this huge tank, which is surrounded by over 10,000 phototubes. And about now, approximately 40 years ago, 35 years ago or so, this detector was built and filled up, and the phototubes put in there and left in the dark. And what this detector was designed to do was to detect, if you wish, the instant of creation. Because the what they were looking for was a process that would create matter where there was no matter initially. And that is obviously an exotic process, because if matter could suddenly come into being and then disappear, we wouldn't be around. Protons, the particles that make us up, as far as our standard model of physics tell us, are absolutely stable. So protons can't decay. But if there's a process that allows protons to come into existence where they weren't there before, then protons can ultimately decay. Now, we know from observations that obviously protons don't decay very quickly. In fact, we know that the lifetime of the proton is certainly longer than the age of the universe. And in fact, from various other experiments you could perform, you knew that the lifetime of the proton was very, very, very long. And in fact, in order to avoid the experimental constraints on the lifetime of a proton and the process of creating matter when there was no matter at the beginning, we know that those processes are so weak that the protons in our body must live at least 10 to the 32 years. Okay, that's much longer than the age of the universe. So if you want to look to see if protons can decay, you obviously can't take a single proton and wait for 10 to the 32 years, but what you can do is use the laws of probability. And if you fill a tank with 10 to the 32 protons, say 50,000 tons of water, then if you put it in the dark, on average, you might expect once per year a proton to decay and produce a flash of light. So that's what this Kamiokande detector was designed to look for, because they were looking for a process that would take the universe from a universe which had equal amounts of matter and antimatter to one that had a slight asymmetry. And I want to explain this. So here's schematically the universe. In empty space, there is about 1 proton per cubic meter in empty space. Many more protons per cubic meter where I am and where you are, but in empty space, 1 proton per cubic meter. And that is enough to account for all the matter that we see in the universe today on average, adding up over the entire visible universe. But what you have to realize is that's not all that's out there. For every proton in empty space right now, there are over 1 billion photons, particles of light. Those particles of light come from the cosmic microwave background radiation left over from the Big Bang, which I'll talk about shortly. But so if you think about it, matter, which is the dominant stuff for us on here on Earth that makes our lives possible, by number is really very rare. There's only 1 proton in the universe for over every billion or 10 billion photons. I'll answer questions, by the way, at the end. I saw someone ask that. So this is a hint to what we think actually happened in the early universe. And the hint was, again, we can measure. This is an experiment near Chicago. You can see Chicago in the distance of this image. And this is before the Large Hadron Collider at CERN, the largest accelerator in the world, the Tevatron at Fermilab, and in near Chicago, Batavia, Illinois. And what would be done here was this accelerator would accelerate particles in one direction and antiparticles in another direction and smash them together to try and see what came out. And what happens when you smash a particle and an antiparticle, as I've indicated, is you produce radiation. Now that leads to the following idea. The 1 proton we see in the universe today, in the early universe, at very early times when the universe was literally 1/millionth of a billionth of a billionth of a billionth of a second old, would have been very hot and dense. And there would have been many particles. There wouldn't have been protons, but the particles that make up protons called quarks, positively charged quarks. And then there are antiparticles, negatively charged quarks, say. And so there'd be this hot, dense soup of matter and antimatter. And all that had to happen was a process that would take, for every billion particles of matter and billion particles of antimatter, it would produce a very small asymmetry, a very weak process that would produce 1,000,000,001 particles of matter for every billion particles of antimatter. Then as the universe evolved, the matter and antimatter could annihilate, but there'd be one extra particle of matter left over and per meter, and that matter would be enough to account for the universe we live in. So we're looking for a process that will very rarely make a very small asymmetry between matter and antimatter, and between baryons, the particles that make up matter, protons and antibaryons. And that is precisely what that experiment in Geneva was designed to do. Because if that process happened in early times, then that experiment might be able to one day see a proton decay, giving us indication that that process of creating matter where there was no matter initially could happen at a very weak rate, but enough to produce a very small asymmetry of matter and antimatter in the early universe. And that, I would say, is the instant of creation. Because in the very early universe, if there were equal parts of matter and antimatter, the universe would be destined to never have life in it. But then at some very early time, a process created a slight asymmetry between matter and antimatter, and it was an accident. It was an accident process that basically the laws of probability said on average there'll be more particles of matter than antimatter, and it would have been so subtle because there'd be an excess of one particle of matter for every billion particles of matter and antimatter that had anyone been around at the time to notice, you wouldn't have been able to notice. It was such a subtle process. But once that process happened, if you wish, the rest of the history of the universe and life and our lives was ingrained. That, in some sense, was the moment of creation. And we think that probably happened around the time when the universe was a millionth of a billionth of a billionth of a billionth of a second old. So that was the point where suddenly matter, the universe became matter, would be destined to become dominated by matter, and all the antimatter in the universe would more or less disappear. Now, there were still no atoms at that time. There were quarks and the particles that make up protons and the particles that make up neutrons, and there were electrons, but there were no atoms. And really, the next important step in the history of life and atoms and our oxygen, ultimately our oxygen atom, would have happened much later than 10 to the minus 35 seconds, almost an eternity later, when the universe was a few seconds old. Another cosmic accident happened. At this point, when the universe is a few seconds old, the temperature is now about 10 billion degrees. Protons and neutrons now exist. Quarks have combined together to make protons and neutrons. But the neutron, which by the way is the dominant elementary particle inside your body and mine, is unstable. If I take a free neutron and hold it here, on average the neutron will decay in 10 minutes. Now, if that was all the case, then we wouldn't have complex atoms that we have today. So here's what would have happened if free neutrons and free protons were just sitting around. After a few seconds, the red particles are the neutrons, the blue particles are the protons, the white particles are the neutrons that have decayed into protons. So some of the neutrons will have already decayed. If you wait 3 minutes, more of them will decay. If you wait 30 minutes, all of the neutrons will have decayed, and all that'll be left is protons. That's all that'll be around in the universe. And that wouldn't be good for building up complex elements and atoms. But a remarkable thing happened. And that remarkable thing was what we recreated in, I guess, 1952 with the first explosion, the first thermonuclear weapons explosion called Mike. During that moment, it was not designed as a science experiment. It was designed as an experiment of destruction, and it destroyed a Pacific atoll. But in that instant, when that nuclear fusion happened, those nuclear reactions happened, almost every element that's ever existed was briefly created in that explosion. Nuclear reactions change history, not only just the history of humanity, but the history of the world. So what actually happened was at 3 seconds, some of the neutrons in our early hot, dense plasma of neutrons and protons and electrons, light, some of those neutrons would have decayed. But then at 3 minutes, what would have happened is that now, before they could decay, some of the neutrons would have combined with protons to form the nuclei of heavy hydrogen called deuterium. And while neutrons are unstable when they're free neutrons, when you put them inside of a nucleus, they become stable. And what would have then happened if you had deuterium, other nuclear reactions would happen. And after about 5 minutes, you would have enough of the protons and neutrons combined together, so you'd have one helium nucleus, as well as the rest of those protons around. So what happened in the first 5 minutes of the history of the universe was neutrons combined with protons to form deuterium, and then helium, and then the process basically ended. Now, this happened when the universe was 10 billion degrees in temperature, and those temperatures are temperatures we can reproduce in the laboratory. So we can measure these nuclear reactions, test how fast they are, and we can predict things like how much helium would have been produced in the early universe. And this is one of my favorite figures. I actually have this as a wallet card that I keep in my wallet, and I show people who don't believe in the Big Bang. These are the predictions for how much helium should have been produced in the early universe, deuterium, helium-3, and the next lightest element, lithium. And you see they vary by 10 orders of magnitude. That we predict that roughly 25% of the universe should be helium, and only one part in 10 billion of the universe or so should be lithium. But what's amazing, if you look at this shaded region, is when we actually try and measure the amount of helium, measure the amount of lithium, measure the amount of deuterium, it all fits. The predictions, which vary by 10 orders of magnitude, are in great agreement with observations, telling us, for those who ever doubted it, that the Big Bang really happened. So, in the first few minutes, the light elements, hydrogen, helium, and lithium were created. But that was it. The nuclear reaction stopped at that point as the universe cooled down. And if that were all there were, there'd be no heavy elements that make up you and I, the important elements for life, like oxygen, our oxygen atom, carbon, nitrogen, iron, all the things that we may be looking for as we look for life elsewhere in the universe. And so the universe itself did not create the elements that make you and I up. That waited for quite a while. Now, after the first few minutes, nothing really happened. In fact, there was about 100,000 years of solitude, to play off a very famous book by a South American writer. Nothing happened. The universe continued to just cool from 10 billion degrees to 1 million degrees, down to a point where the universe was about 3,000 degrees. And at 3,000 degrees, something very important happened. Before 3,000 degrees, there were no atoms. There were the nuclei of atoms, helium and lithium. But if an electron tried to be captured by the nuclei of an atom, the radiation was hot enough that it would kick the electron out again. So there were only ions. But when the universe cooled down to 3,000 degrees, protons could capture electrons and suddenly create neutral matter. For the first time in the history of the universe, neutral atoms existed. And that was a very important time because, you see, when the universe was a charged plasma, light interacts very strongly with radiation, and the universe was essentially opaque to light. But the minute the protons captured the electrons and matter became neutral, suddenly light could propagate throughout the universe and it became transparent. And we can actually look back and see that time now. If we look out from the Earth and we look out at galaxies, so here's the Earth, and this is a radio telescope looking out at distant galaxies, maybe 1 billion light years away. We look back at time by 1 billion years. If we keep looking back earlier and earlier in time, the universe would be getting hotter and hotter and hotter until we look back to a time when the universe first became transparent. We can't see any earlier times because the earlier universe was hot and dense and charged. So what we would expect to see is radiation coming at us from that surface when the universe first became neutral. That radiation was a temperature of 3,000 degrees back then, but as the universe has expanded, it's cooled, and we would expect to see a radiation bath now. Since the universe has expanded by a factor of 1,000, we'd expect to see a radiation bath about 3 degrees above absolute zero. And that was what was discovered by accident in New Jersey, of all places, in 1965. But we've now been able to take images of that radiation. And these images have won several Nobel Prizes already, in fact. But here is an image of that radiation coming at it from all surfaces. This is a projection, just like the projection of the surface of the Earth. I can project a two-dimensional sphere into a plane. Well, I can project that sphere 10 billion light years away in all directions into a plane. And when I do that, I get this image. And the horizontal is where our galaxy is, and that's been removed from this image. And this is the radiation coming from the Big Bang. What you see here is a radiation, and we can measure its temperature, and it's incredibly uniform. It's about 2.7 degrees above absolute zero, as we would predict. And there are little hot spots and cold spots. But the hot spots and cold spots differ from each other only by about 1/100,000th of a degree. So it's incredibly uniform, except for very small variations. But those small variations were important, because basically that set us up for the future history of the universe and the future history of our atom, our oxygen atom, which, by the way, doesn't yet exist as an oxygen atom at that time. But what happens at that instant is the eternal war between gravity and pressure begins right there. Because once matters become neutral, radiation pressure, which, if radiation is interacting strongly with charged matter, stops matter from collapsing. When the matter becomes neutral, that radiation pressure goes away and matter can begin to collapse due to gravity. And that eternal war between radiation pressure and gravity began then, and it continues today, and it governs everything that governs our existence, including the origin of life. But gravity will eventually win, as we'll talk about. It hasn't won yet, which is why you and I are still around. But for now, those small lumps, those small perturbations and representing little lumps of matter begin to grow because matter begins to collapse after the universe is 300,000 years old, when the temperature of the universe is 3,000 degrees. And for millions and millions of years, those clumps collapse and collapse and collapse. And it may take 500 million years or close to 1 billion years, but eventually those lumps begin to collapse and the gas begins to heat up and collide and fragment. And eventually smaller clumps begin to collapse and collapse and collapse. And at a time somewhere between 500 million years or 1 billion years into the history of the universe, the first stars form. These are images of star-forming regions. And when stars form, the gas collapses and becomes very hot and intense. Here's an image, a sort of filmed image of an early star forming. It's an incredibly violent process. And these early stars can be about 10,000 times brighter than our sun. But they're not yet stars. They're protostars, because they don't become stars until the matter collapses and collapses and collapses until the center of the star becomes hot enough that nuclear reactions begin to take place. And that's what distinguishes a planet or just a bunch of mass, a gas cloud, from a star. A star is hot enough so that nuclear reactions begin to take place in the center of that star. And those nuclear reactions are responsible for the creation of basically all of the components of life. So this is a short history of stars. And this, I want to give this history. It's a history of a very massive star, about 10 times more massive than our sun. Our sun's lifetime will be about 10 billion years. But for a star 10 times more massive than our sun, its lifetime is 1,000 times smaller. So it's only 10 million years. And what happens is the star begins to collapse, and then eventually it gets to the point where nuclear reactions begin to take place, and helium and hydrogen atoms will fuse. The same process that produces thermonuclear bombs will fuse to produce helium, releasing an incredible amount of energy. And that's what powers the stars, like our sun. But for a very massive star, that process, the hydrogen burning, will only last about 10 to 15 million years, unlike our sun, where that burning will last 10 billion years. What happens when the hydrogen has been used up? Well, suddenly the fuel source for this that's holding the star up begins to go away, and the core of the star begins to collapse. It heats up making the outside of the star get much larger. That actually causes it to become what's called a red giant. But eventually, the core of the star begins to become so hot that helium begins to burn to form carbon. Another process that is much less efficient than hydrogen burning, and therefore the star is much hotter and burning much faster in order to make it happen. And the whole process of turning helium to carbon takes about 1,000,000 years. What happens then? Well, the helium's used up and the core of the star begins to collapse again and get hotter. But then carbon begins to burn its nuclear as a nuclear fuel to form neon and then oxygen. And that process of carbon burning takes about 100,000 years. The star is now burning furiously just to keep from collapsing. In order to generate enough energy to keep from collapsing, it has to burn up all that carbon in only 100,000 years. Then oxygen, when the carbon's gone, the oxygen begins to burn. It takes 10,000 years for that oxygen to form silicon, and that is the last day in the life of the star. Because it turns out silicon can burn to form iron, but it does so. At that point, the star is so dense in the core and so hot, burning so furiously that all of the silicon in the core of the star is burned to form iron in a single day. And then the star's life is over. Because iron is the most densely bound nucleus in nature, and iron nuclei can't form and fuse to form heavier elements and release energy. It takes energy to do that. Before that, every time hydrogen, helium, carbon, oxygen burned, when they fused, they created immense amounts of energy, like thermonuclear weapons. But iron can't burn. So in the last day, suddenly the core of the star burns to form iron. And at that point, the star, that's the last, literally 10 seconds in the life of the star, or second. Because after the silicon fuel is gone, the core of the star, the iron core, collapses. And it collapses under its own gravitational weight, if you wish, so fast that the entire core of the star goes from something the size of the Earth to the size of Rio de Janeiro in about 1 second. And then it becomes so dense when all of that mass is now the size of Rio de Janeiro that basically you have a single incredibly dense atomic nucleus. And that nucleus is so dense that it can't collapse any further, and that forms a shock wave. All that material collapses until suddenly it can't collapse any further, and that shock wave spews out all of the material like onion shells, the hydrogen, the helium, the carbon, the oxygen, the silicon. It's all sent out into space in an incredible explosion called a supernova explosion. And that all those materials get sent out into space later on to seed the formation of other stars. And I said this in a different lecture in the context of my book, A Universe from Nothing. But every atom in your body went through this process. Every atom in your body has experienced the most violent explosion in nature, a supernova. Because it turns out the atoms on Earth probably went through many stars and were processed in many stars before eventually, as I'll talk about, the formation of our solar system. And therefore, atoms in your left hand may have come from different atoms in your right hand. You are literally stardust. And we are literally stardust. So when we're looking for life in the universe, we are the universe. What's out there is intimately connected to us. And I think that is one of the, as I've said before many times, it's one of the most poetic things I know about nature. Now, here's a recent supernova, relatively recent, called Supernova 1987A. It was the last supernova seen in our galaxy. Supernovae occur about once every 100 years per galaxy, but most of them are invisible in our galaxy because our galaxy is full of dust and we can't see them. But this was a supernova in a nearby galaxy called the Large Magellanic Clouds, which you can see in the southern hemisphere, not in the northern hemisphere. And in that Large Magellanic Clouds, that star here exploded on, I think it was February 23rd, 1987. I can't remember the exact day in February. I remember it at the time because it was very important in physics. And we could see that explosion. And those explosions, here's a remnant of a supernova explosion, the Crab Nebula, which the supernova that was observed in about 1066, I think. And this is the remnants that have gone out. And as that material is thrown out, it collides with the interstellar medium, compressing it, causing it to shine, but also helping create other stars.
I didn't hear what you said.
And here's the, if you look very carefully here, let me go back. If you look in this image, you'll see the original supernova, and now 40 years later, you can see a ring of material where that shock wave is going out into the interstellar medium. And when that shock wave of material goes out into the interstellar medium, it creates other stars. And this isn't a painting. This is an actual image of a star-forming region. When a supernova explosion goes off, it seeds the formation of other stars by compressing gas and creating new collapses and new stars. And in our region of the galaxy, and those new stars, by the way, begin to not only collapse, but material around them begins to collapse, causing what's called an accretion disk. And until about 25 years ago or so, 20 years ago, theoretical physicists like me would say, yes, those accretion disks will form planets, and we think most stars will have planets around them. So there should be lots of planets out there, but we didn't know for sure. But as you probably know, we have since discovered, beginning 20 years or so ago, planets around other stars. And we now have discovered thousands of planets around other stars. And it validates our prediction that every star more or less should have an accretion ring around it. And pretty well every star should have a solar system around it. So there are 100 billion stars in our galaxy, and there are probably 100 billion solar systems. And from the point of view of searching for life, that's an incredibly important thing. But what happened of more importance for us in particular was now that a supernova went off about 5 billion years ago in our region of the galaxy, compressing gas and forming that gas cloud to begin to collapse, eventually forming what would become our sun and an accretion disk around it, which would eventually contain the material that would form all the planets of our solar system. In that accretion disk is all the basic materials that would later be relevant for life, including the oxygen atom that was in this glass that I just drank from the water in this juice. That oxygen atom was created in a supernova explosion 5 billion years ago and had been going through space, eventually to be caught up in the collapse of a solar system. And it might have been in the outer regions of our solar system. Now, fortunately for us, our solar system has Jupiter in it. Because as the Earth formed and as the planets formed, there was material was coming together and colliding and colliding and colliding, and around our Earth, asteroids and meteors and comets would be impinging upon the Earth, large ones, and colliding with our Earth every million years or so. And if that were the case, no life would have been able to form on Earth. But fortunately, Jupiter started to form and started to gobble up all the material that would have otherwise been asteroids or comets that would hit the Earth. It would either gobble them up or it sent them into the outer solar system. Jupiter, which is 1,000 times the mass of the Earth, allowed for life to be possible on Earth because over the period of about 100 million years during which Jupiter formed, the collisions of material and bombardment of material on the Earth's surface went down exponentially. Until about 500 million years after the Earth formed, the bombardment was low enough that life could form. Now, here are the comets that we see in the sky. These would have been bombarding the Earth. One of the interesting things is, one of the central questions we still have is, where did the water on Earth come from? After all, the Earth formed in a region of the solar system which was incredibly hot at the time the Earth was forming, 1,000 degrees. Water is volatile. You might not expect water to be on the Earth. Now, we think now perhaps a lot of water was trapped in the rock that eventually did form the Earth. But certainly one interesting thing is true. Enough water has been transported to Earth from comets, from frozen objects from the outer solar system over the Earth's history to account for all the water in the Earth's oceans. But we know that that's not exactly what happened, or we're reasonably certain. Because if we look at the isotopic composition of the water in comets versus the isotopic composition of the water on Earth, it's not exactly the same. And this still remains somewhat of a mystery. A lot have been resolved in the time since I wrote this book about 20 years ago. But one of the places we're looking is looking at other places. Here is an artist's rendering of a huge asteroid or meteorite hitting the Earth, which may have brought water with it. At the time, of course, had it hit the Earth, had life been around, it would have destroyed life on Earth. This bombardment stopped, but I'm imagining sometime around 100 million years after the Earth formed, a comet carrying our oxygen atom in it, in the form of frozen carbon dioxide, slammed into the Earth 100 million years into the Earth's formation. But where did the water come from? One of the places we're trying to find out where the water came from is by looking at a place like this. This is an early image from an early rover. This is not Los Angeles, it's Mars. And we're looking, one of the many reasons we want to explore Mars is to look for water on Mars, and clearly to look for potential evidence of life on Mars. It's the number one site, and as you know, there are rovers right now, the Perseverance rover on Mars, that's now looking for evidence of early, perhaps fossilized life on Mars. But one of the things we're quite interested in is the composition of the water on Mars. But one of the ways we may learn about Martian rocks is not just by sending rovers up, but by going to another place that looks a little like Mars here. It's Antarctica. Why? Because in Antarctica, we can find little bits of Mars. Because in fact, no planet is an island in our solar system. When comets and asteroids hit the surface of Mars, they knock material out, and some of that material falls towards the Earth, entering the Earth's atmosphere as small meteors. Now, why do we go to Antarctica to look for these objects? Not because they preferentially form and fall in Antarctica, but Antarctica is white. And if you're traveling along a snowmobile, driving along on the surface of Antarctica, and you see a rock, it came from up there. Thank you. It came from up there. And so this here is an example. In fact, this is a rock, a meteorite, which is very important, discovered in the Allen Hills of Antarctica and examined in the 1990s. Is ALH 84011,65. But what it is, when this object, which is a Martian rock, a rock that we know from its composition is from Mars, was analyzed under electron micrographs, images like this were observed, and this caused great excitement from some chemists at Stanford and other places. And in fact, the President of the United States at that time, Bill Clinton, planned a press conference to point out this was the first discovery of fossilized life from another planet, because it looked very much like the oldest fossils we can see on Earth, which are about 4 billion years old, which don't look very different. The problem is images can be deceiving. The size of these spheres is maybe 1/1000th the size of these spheres. And since that object was discovered, chemists and geologists have realized that non-biological processes can produce these images. But it may happen one day that we discover fossilized life from Mars that looks like the earliest fossils on Earth. And then you have to ask yourself the question, did life on Earth originate on Earth, or did it originate on Mars? In fact, if you want to know what a Martian looks like, you might want to look in the mirror. These are all open questions that remain to be discovered, relevant and interesting for astrobiology, but our atom actually arrived on Earth before life began to form. As I say, the atom that in my story, arrived on Earth merely 100 million years after the Earth's formation. And then it began to be processed through the Earth. And there's a very important process that processes atoms through the Earth, a geological process. Carbon dioxide, and by the way, the early Earth's atmosphere was mostly carbon dioxide, a very important fact. There was no free oxygen, as I'll point out in a moment. But that carbon dioxide dissolves in water, creating what's called carbonic acid. It's the reason that when you open a can of soda, the carbon dioxide in there that's under pressure is dissolved in the soda, and it produces a tart flavor, which is carbonic acid. And eventually, if you leave it open for a while, the carbonic acid will go away and the soda will get flat. But the carbonic acid would then eat away at calcium carbonates, calcium materials in rock, and create calcium carbonates, which would go down to the ocean floor. But due to plate tectonics, that material would then be subducted into the earth, and that would build up carbon dioxide in the earth, and eventually that carbon dioxide would be spewed out by volcanoes. And this cycle, this carbon cycle, the natural carbon cycle of geology, takes about 100 million years to cycle carbon dioxide atoms in and out of the earth. And our oxygen atom in a carbon dioxide molecule fell to earth, was precipitated in, and over 200 million years or so processed in the earth before it being spewed out. And the world after it spewed out was very different than the world before it spewed out, because in that interim, life had begun to form. We think life potentially formed first in the deep oceans. This is a dark smoke or a black smoke. This is rich material spewing out in deep underground caverns in the deep ocean that are rich in a variety of materials. And we think well before the processes of life metabolism that we see now, which is based on what's called ATP and the conversion of carbon dioxide to oxygen, that early processes of life probably happened in the deep ocean floor. But very quickly, life began to learn to use a different process, photosynthesis. Now, the really important thing, and this is relevant for astrobiology, is that in the early Earth, there was no free oxygen. If there were free oxygen, we wouldn't be here, because oxygen is a poison initially. Oxygen burns things, and life is nothing other than the controlled burning of organic materials. But if free oxygen had existed on Earth, all the organic materials on the surface of the Earth would have been oxidized early on, and the process of burning that now powers our existence, that very slowly by life, would have been done quickly, and there wouldn't be materials left to as the basis of life. So there was no free oxygen. The free oxygen on Earth was created by life, because early single-celled organisms, and these are called stromatolites, which you can find in Mexico, or these are ones from Western Australia. Single-celled objects had discovered how to harness the power of the sun by photosynthesis to produce energy to power their metabolisms. And of course, as you know, one of the processes of photosynthesis is to take carbon dioxide and water and turn it into oxygen. And over billions of years, these little beasties would produce little puffs of oxygen, which was a poison to the ones on the surface. So they would die off, and then new ones would have to grow. And that's why these stromatolites grow, each one sacrificing itself and its neighbors for the good, ultimately, of the system. And ultimately, over several billion years, these little single-celled organisms would puff out little bits of oxygen, raising the oxygen level ultimately to about 1 billion years ago to the level of oxygen we now have. About 20% of the atmosphere is now oxygen. Now, life existed in many different forms of single-celled creatures in this time, but no animals. It's easy to harness the power of the sun, but photosynthesis alone does not harness enough energy and release enough energy to be able to power animals like you and I, or to build bones that can be the backbones of objects that move. Life had to learn another process, and probably did in the case as often happens with evolution. There was a catastrophe about 800 million years ago. The Earth froze over. And probably during that time, life had to explore new mechanisms to survive. And the mechanism, of course, that life was able to exploit was not photosynthesis, but respiration. There was now enough free oxygen in the atmosphere. Our oxygen atom could now have been turned from carbon dioxide into oxygen, and now could be used and breathed in by living forms to power to produce about 37 times more energy than photosynthesis can. That energy stored in molecules called ATP, which is the universal fuel of all life on Earth. One of the many reasons we understand that all life originated from a single process, from a single organism. But once life had harnessed oxygen by respiration, 37 times more energy could be produced, and that allowed for the existence of animals. And we begin to see in the Cambrian explosion animals with shells, and we begin to see the first fossils, the first clear examples of complex systems. And over the next billion years, basically not much changed except the evolution of more and more diverse sorts of animals. So even 500 million years ago, the atmosphere of the Earth was not very different than it is now. The surface of the Earth was replete with plants, and except for the type of flora and fauna, the Earth wasn't a very different place. So the Earth became a green, living planet. Not yet with us on it, but our oxygen atom was now experiencing a very different cycle. Previously, it had cycled through the Earth once every 200 million years, but now, through the processes of photosynthesis and respiration, in the period of years, our oxygen could be cycled back into carbon dioxide and into oxygen and back into carbon dioxide, back and forth, powering the process of life. And that was the case for our oxygen atom for a long time, until humanity came about. This, by the way, is what in the absence of humanity is how carbon dioxide gets transferred around the planet. The outer process is the process I talked about with carbon dioxide being dissolved in the oceans, going into the deep earth, and coming out in volcanoes. You see, only very small amounts of carbon dioxide are processed per year, about 1/100th of a gigaton of carbon. But the processes of life transfer much more carbon dioxide to the atmosphere. Over 100 billion tons of carbon is transferred back and forth between the atmosphere and the oceans due to life, in the absence of humanity. We'll get to humanity in a bit. So our oxygen atom is experiencing all of these life processes much more frequently than it would be experiencing these geological processes. Now, I'm getting near the end, believe it or not. We started a little late, and it took me a little while to get going. But I want to, as we get near the end, we're almost at the present, and then we have the future of the universe. But we can do that very quickly. This is the present. If I could see the audience now, I'd ask you, who is this person? And some of you, since you may have a classical education, would know that this is Julius Caesar. Now, I want to ask anyone who's still listening to hold in their breath. Hold it in and don't let it out till I tell you. Keep holding it. Keep holding it. Keep holding it. Now let it out. Okay. In that breath, every single breath you take, we can calculate. It's one of my favorite calculations I do with first-year physics classes. We can calculate that every time you breathe in, you're potentially breathing in up to, say, 10 atoms from the dying breath of Julius Caesar when he said, "Et tu, Brutus." But not just Julius Caesar, everyone who ever lived, because that carbon cycle in the earth of oxygen going to carbon dioxide back to oxygen recirculates and recycles your oxygen through the atmosphere in a period of less than 50 years or so. So every time you breathe in, you're breathing in atoms from pretty well almost everyone who ever lived, friend or foe. Our oxygen atoms, if you wish, connect us. You are literally made up of the atoms of everyone else who's ever lived on Earth. And that should remind us that we're a global species in these times when we have nationalism and violence and wars and civil wars and terrorism. We should really remember that we're actually all made up of the same atoms from each other. not only are we made up of atoms of stars, but we are made up of atoms of everyone else. And that gives me solace, because there are days when I'm working in my physics and I'm not getting anywhere. But I remember that when I'm working, every time I breathe in, I'm breathing in some atoms from Albert Einstein, that Albert Einstein breathed out the moment he finished his general theory of relativity. And that makes me happy. So you can use this idea to make you happy or sad, depending upon what you want. But it's true that literally your oxygen atoms have been through almost everyone who's ever lived. And in fact, the oxygen atoms that I'm breathing in now were first produced as free oxygen by these stromatolites billions of years ago. So really, the oxygen atoms I'm breathing in have not just been recirculated through every human that's ever lived, but through every animal that's ever lived, every oozing, slimy animal that's ever lived, or these stromatolites. And here's a picture of a much younger version of me many years ago with Lucy, the famous hominid, 3.4 million year old hominid discovered in Africa. And I like to think that every time I breathe in, I'm also breathing in atoms that Lucy breathed out. And that I find very poetic as well. Actually, one of my favorite lines from Macbeth from Shakespeare is the favorite line, you may remember, after he kills the king, tries to wash his blood, and says, will all great Neptune's oceans wash this blood clean from my hand? No, this my hand will rather the multitudinous seas incarnadine. And what he meant by that was, my hand will make the seas red. That's what he felt like, because he couldn't get rid of the blood. Well, that's not true exactly, but if you prick your finger and take a little bit of blood and put it in a spoon and take it to the ocean, like the river that right behind me that goes to the ocean, a year later, if you come back to the ocean and take a spoon, you'll find that probably there are some 1 or 2 atoms from your blood that have now recirculated throughout the whole ocean. And so every time you drop something in the ocean, the atoms circulate all over. We're connected all throughout the planet, and as is our oxygen atoms. Now, I showed this image before, and I just can't help, because I wrote a book called The Physics of Climate Change, to point out that this carbon cycle, which has been existing for billions of years on Earth, has changed because humanity every year is dumping 10 gigatons of carbon into the atmosphere, not by just its standard living, but by extracting out of deep earth reservoirs fossil fuels and burning them to power civilization. And that will change our own future. As you know, it's producing a climate crisis, and how humanity deals with that will be one of the things I think that will determine, in some sense, the future of humanity. Not that climate change is going to destroy humanity, but it might create tensions, geopolitical tensions, that could cause humanity to destroy itself. Either way, it doesn't matter, because life on Earth is finite. In about 5 billion years, the sun is going to burn up all of its hydrogen fuel and begin to become a red giant. When it does that, it will engulf the Earth. And whether humanity's been smart enough to survive or not doesn't really matter. There are 2 options. At that time, it will blow off and evaporate the entire atmosphere of the Earth. Now, as far as our oxygen atoms are concerned, it doesn't really matter. Because you see, if we're living as a civilization and we die then, well, we'll be vaporized and our atoms will go out into space. But if we've already died off before then, our oxygen atoms will still be in the atmosphere and will go out into space. So as far as the future of our oxygen atoms are concerned, it doesn't really matter. Their future is in space. Now, you might say, maybe we'll be really smart and leave the Earth before that happens. Maybe populate Mars or somewhere else. Well, the point is, again, as far as our oxygen atoms is concerned, the future is not very different. Whether we take our oxygen in rocket ships to different parts of space, or whether the sun blows out the atmosphere, our oxygen atoms, the ones that were in the glass of water that I'm drinking, their future will be in the stars. And there are other things that will happen too. Not only will our sun in 5 billion years basically destroy the Earth, but the Andromeda galaxy, which is the nearest large galaxy to our own, is heading at us at about 100 kilometers per second. And in about 5 billion years, it will collide with our Milky Way galaxy. Now, it turns out galaxies are mostly empty space, so very few stars will hit each other. but there will be disturbances, and that will knock planets out of solar systems and other things. So the future is miserable as far as our life is concerned. But as far as our oxygen atoms are concerned, the future isn't so bad. They may go out into space to one day be captured by a gas cloud that's collapsing to form a new solar system, which one day may have new life forms. And as far as our oxygen is concerned, that process can go on for a very long time, for literally trillions of years, because the longest lived stars in our galaxy will live about 10 trillion years. And after that, the stars will die out. As far as all of the evidence of our human civilization here on Earth, however, except for anything we take with us, if we're lucky enough to survive as a species, all of that will disappear. When the sun goes red giant, any evidence of life on Earth will be gone because the Earth will be engulfed, and our story of life, of our human life, will have ended. But for our atoms, as I say, the future is not so is brighter, if you wish. Our atoms might become part of another life form, or they might become part of might fall in near a black hole. And near a black hole, there are jets that send material out at very fast speeds. And so I like to think that the oxygen atom that I was just drinking will one day be caught up in a galactic jet from the center of our galaxy that will spew it out into empty space. And our atom will go on traveling through empty space for what seems like an eternity, but it won't be an eternity. Because remember, eternity is a long time, especially near the end, but our atom's eternity is not a full eternity because, remember, protons, we think, decay. So eventually, after an unbelievably long time, 10 to the 32 years or so perhaps, all of the material that makes up stars will begin to decay, and the universe, all matter in the universe will disappear, and producing radiation which will cool as the universe expands, and the universe will become cold, dark, and empty. And that is the end of the future for our atoms, and the end of the future of pretty well everything in our universe, and the universe will end badly then. But we should enjoy our brief moment in the sun. As we think about the highs and lows of human civilization and the possibilities of civilizations elsewhere in the universe, we should remember not only are we stardust, they're stardust, but we are connected to the entire history of the universe through our atoms, and all life is connected in that way. We are stardust, so are they. We share a common cosmological origin with all life in the universe, whether it's life on Earth or whether it's life that we may discover elsewhere. So that's a story of our atom. And our life, the story of our atom in our life, was just a brief speck of time in the history of the full story of the oxygen atom. We are just a brief speck in the history of the universe, maybe not a significant speck. We make our own significance, and we should enjoy our brief moment in the sun. Thank you. So, I'm ready to answer questions.
It was an amazing presentation, Professor Krauss.
Thank you.
Thank you for your presentation.
If anyone's still there, and if there are anyone who has any questions.
Can I go?
Yes. We have any question, Krauss, that you can pick?
Yes, we have some questions here, Professor. By the way, excellent lecture. I was really impressed. It's not my area, but it made me think.
Good. Well, that's the point. If it made you think, my job is done. Thank you.
Yeah. Thank you. Thank you for this presentation. Well, the first question we have here, it was asked by Vic. She's asking about when the first atoms started to appear, if they started releasing cosmic background radiation, and during this moment, how did the matter and energy begin to behave?
Okay, that's a very good question. When the first atom, you have to understand the radiation was already there. At that time, before the first atoms, neutral atoms formed, you had protons and electrons and radiation. And I'm going to make this so I can, it'll autofocus on me. There we go. Okay. And we had So protons and electrons and radiation in a dense soup, and it was all strongly interacting with each other. What happened was the protons captured the electrons, forming neutral atoms, and that allowed the radiation that was already there to move freely throughout the universe. So it wasn't as if the atoms released the radiation, they periodically absorbed it and scattered it, but most of the radiation was already there, and it was just suddenly released and flowed free throughout the universe. And it's still about 300 photons per cubic centimeter in every part of the universe, a cosmic wave pattern. In fact, if you unplug your television and from any of its receivers, you'll just see static on the TV screen. And about 1% of the static on your TV screen is radiation from the Big Bang. So when we say, well, how do the atoms behave? For the most part, the radiation just went through without scattering the atoms at all. Every now and then, some radiation would interact with an atom, exciting it, and the atom would then de-excite and emit radiation. Sometimes it would ionize it. But then as matter began to collapse, of course, it heated up and became ionized. And then in the center of galaxies, that radiation will interact with that hot ionized gas, because that ionized gas is now ionized and it can interact with the radiation. And so eventually, once the universe formed lots of stars, that the universe again became kind of almost opaque to that radiation. The radiation couldn't make it through there without interacting once or twice. And we're trying to measure that first light, that first cosmic dawn, if you wish, called the era of reionization today. It'll tell us of the period of star formation.
Okay. Can I go for the next question?
Sure.
Okay. I'm going to continue with Vicky because she asked 2 questions. She asked if you have any work, article, book, research that you have done or that is related to this subject and that you would recommend.
Well, that's a good question. I'm glad you asked it. And the answer is, of course, yes. The lecture I just gave is a quick summary of one of my favorite books that I wrote, which is available in Portuguese, by the way. And it's called Átomo in English, an odyssey from the Big Bang to life on Earth beyond. I wrote it about 20 years ago, maybe a little more. And it contains that story and a lot more. But also some of the stuff I talked about having to do with cosmology was in my more recent book, which has been very popular, which is also in Portuguese, called in English, A Universe from Nothing. And so that's another book it was in. And then my discussion of the carbon cycle is in my most recent book, which I do have here because I just happen to have it on my desk, The Physics of Climate Change, which isn't in Portuguese. It's being translated into Spanish and French, but not yet Portuguese. So get your publishers to want to translate it into Portuguese.
Very good. What is the name of the last book you just told that we don't have in Portuguese?
It's called The Physics of Climate Change.
The Physics of Climate Change. Okay.
And I don't know what that would be in Portuguese. What would it be in Portuguese?
Física das Mudanças Climáticas.
Well, there you go.
There we have a title now.
Yeah, we have a title. Now we just need the book to go along with it.
Okay, very good. There is another question here by Nathaniel. He's asking, what do you think about the importance of the increase in astrobiology's popularity in these last years?
Well, it's a good question, and I want to give an answer that may surprise some people. I think astrobiology is a field which is obviously it's incredibly important because it one day may answer the question we all want an answer to, which is, are we alone? Obviously, one of the questions that everyone asks, are we alone in the universe? But it's also a field where really there's very little data and a lot of speculation. It's very early in the field, and I kind of worry when I see results presented from astrobiology as if they're definitive. You've got to remember, we don't know the origin of life on Earth. We don't know the processes that led to the origin of life on Earth. We never observed any evidence of life elsewhere in the universe. We don't even know what the locus of possibilities are. So this is an area where basically we know almost nothing. And often I see in the popular media presentations of discoveries that make it seem definitive that we know that this planet is habitable. We don't know it's habitable just because it might be in the habitable zone of a star, meaning it has liquid water. Because in fact, the Earth, which we know is in the habitable zone of the sun, was once frozen solid too. It depends on the Earth was frozen solid because the continents were in a specific orientation, so the albedo of the Earth changed and it reflected more light and cooled down. And so none of these processes are considered generally in astrophysical and astrobiological modeling. So I think astrobiology is a field where it's kind of premature for many of the results that are claimed to be made. It's an incredibly exciting time because we're beginning to finally discover planets around other stars and maybe one day be able to image those planets and explore their atmospheres. We've already been able to look for certain molecules in the atmospheres of planets. So it's got a great future, but I think it's in its infancy right now. And I think we should, those of us who are scientists and in members of the public, should take many of the claims of astrobiology with a grain of salt right now. It's really too early to make definitive statements about the existence or non-existence of life in the universe, the processes by which life evolved, and even the different kinds of life that may form in the universe. It's all pure speculation.
Okay. There is a question here that I found very interesting. Let me see if I find it. Okay, actually, there are two questions here. The first one I would like to ask is from Felipe. He's asking if there is any possibility, considering the scientific method and current cosmological theories, that there are multiverses, and what are your thoughts about it?
Well, it's a very good question, and in fact, my book, A Universe from Nothing, is a large part of the end of it is about multiverses. Our current best ideas about cosmology suggests it's highly plausible that our universe is not unique, that our universe is one of potentially an infinite number of universes in which the laws of physics may be different in each universe. All of our best ideas from particle physics suggest that different kinds of multiverse, but my mind, well motivated version is called inflation, and in that I don't have time here to go into it, but it's quite likely that there are many causally disconnected universes. By universe, we now mean something different than we did when I was your age. When I was your age, universe meant everything, but now we define universe to mean that region of space with which we can one day communicate, or one day could have, or in the past could have communicated to us. So if we can't communicate with it by light, then it's causally disconnected and we can't have an impact on it. And that those regions of space, there are regions that may be moving apart very fast, which can never ever be in causal contact with us. And in those regions, it's quite likely that the laws of physics may be different. Now, you might say that sounds like metaphysics because we'll never really know because we'll never be in contact. It turns out that there are indirect experiments we can do, and I've written papers on this, that while directly we'll never know about the existence of other universes, there are indirect experiments we could do that would be strongly suggestive to tell us that those other universes exist. They have to do with the measurement of what are called gravitational waves from the beginning of time. And if we can measure those gravitational waves from the beginning of time that come from this process called inflation, then we'll have pretty good evidence that those multiverses really do exist.
Okay, great. The other question, that was the one, Bruno. Do you expect, we are so in sync.
Yeah.
Do you expect the JWST to change our understanding of the universe the way that Hubble telescope did? Or do you think that we are pretty confident in what we are going to see?
Well, the answer is, of course, we don't know, which is why we have to look. If you go by history, every time we've opened a new window on the universe, we've been surprised. So I like to say every day, I'm surprised if I'm not surprised. And so while we have good ideas about what we may see with the James Webb Space Telescope, I expect that the most interesting observations made with the James Webb Space Telescope were things we didn't anticipate in advance, much like the Hubble Space Telescope. So we'll never know if we don't keep looking, which is one of the reasons why we have to keep opening new windows on the universe. If we don't have them, we'll never know. And one of the joys of being human is to ask these questions and have the possibility of answering them.
Okay. There is one here. It was Bruno who asked. He's asking about the proton decay inside the detector in Japan. And you said it will produce a flash of light. And he's asking, how does that work? And what are the implications of this discovery for particle physics?
Well, those are three really good questions. I'll give you quick answers. They're very important questions. They have profound implications for particle physics. And I will mention another book I wrote, the one before this most recent book, called The Greatest Story Ever Told So Far, which is a story of the Standard Model of particle physics. And I believe that book is available in Portuguese as well. It really tells the story of what we might discover if the proton decays. The reason a flash of light occurs is quite simple. If the proton decays, we think it'll decay to lighter particles, like say electrons and or positrons and neutrinos, or particles called pions and neutrinos. But since its mass is much greater than the mass of the particles it decays into, those particles will be streaming out with a lot of energy. And those particles stream out with a lot of energy, they'll bump into atoms and light them up, basically. And so that's what the flash of light that you'll see. But the implication, if we were to see protons decay, would be evidence that the forces of nature, the three non-gravitational forces of nature, the strong interaction, the electromagnetic interaction, and the weak interaction, are all unified in a single theory that we call a grand unified theory, which would really tell us in some sense that at a fundamental level, physics is very simple. And it would bode very well for potentially a theory that might unify all four forces in nature: electromagnetism, the weak force, the strong force, and gravity. So it would be a profoundly important observation if we discovered proton decay. It hasn't been discovered yet. Those detectors have been operating for over 30 years. But one day they may discover evidence that protons decay. And we'll have definitive evidence that a grand unified theory really does exist.
Okay. I have a question here in Portuguese. It was Elisa asking, I'm translating here for you now. She's asking if on Earth we have all the elements from the periodic table, and if we have them present here on Earth, and if it means that all of them were present during the formation of the solar system. And if in the other solar systems, in the other planets of the other solar system, we have the same chemical elements.
Well, it's a very good question. First of all, not all the elements of the periodic table exist on Earth, because once you get past uranium, the elements are all on the table. So the very heavy elements that we know exist on the periodic table live only a fraction of a second, so they're not available stably on Earth. But other than that, all of the elements, certainly up to uranium and even a little bit beyond, exist on Earth. Now, what's really interesting is that different kinds of supernovae, different exploding stars, can produce different ratios of carbon to oxygen to silicon, for example. So the ratios of the abundance of elements on Earth is not necessarily going to be the same as the ratio of all the elements on a planet around a different star that formed out of a different supernova. That planet may have a greater percentage of carbon or less silicon or something else. So while all those elements will exist on all those systems, the percentages of elements may be very different. And some people have speculated, therefore, there may be planets where silicon life forms exist because there's not much carbon, for example. All of that is speculation. One of my favorite episodes of Star Trek had a silicon-based life form called the Horta on it. But the point is that the elements exist, but potentially in different abundances in different solar systems around different stars.
Okay. I have a question here from, Giovanna. She's saying that she once saw another lecture that you gave, and you said that you're just a person that loves to enjoy the sunlight. And do you think that having the knowledge you have has helped you on giving significance to your life?
Oh, what a wonderful question. Yes, in a way. Because what it's told me is that I'm cosmically insignificant. that the universe doesn't revolve around me. But what that tells me, it doesn't make me sad. It makes me happy because it means I make my own significance. It also means I realize that I'm here for a brief moment in cosmic history. Yet I'm here at a time when we can understand the history of the universe to the earliest moments of the Big Bang and the far future. And therefore, I should make the most of each moment in my life to learn about the universe. So what I've learned about the universe has invigorated me and made me want to learn more and appreciate how lucky I am to be conscious in this amazing universe, even if the universe doesn't care about me.
That's very good. Very good. Okay, we have one last question here. It's from Jonas. He's asking if, in your view, it's more likely that the universe is full of simple or complex life? Or is it more likely that life is a very rare event?
Well, I want to answer it by reminding you what I said earlier about astrobiology. The real answer is I don't know. But if you wanted to get me to speculate, I think life is relatively rare, but there are so many there's so many stars and so many solar systems that even if it's rare, I suspect that life is ubiquitous throughout the universe. Simple life. Now, it took 4 billion years of living, 4.5 billion years of living on a planet that's relatively isolated, in a solar system that's relatively isolated and protected from the rest of our galaxy, for intelligent life to form here on Earth. And therefore, I expect that while microbial life is probably abundant throughout the galaxy, including perhaps in the moons of our own solar system, the moons of Jupiter or Saturn, in the deep oceans of Enceladus or Europa. But I think intelligent life is far, far rarer. I nevertheless still think it probably exists out there, but the universe and the galaxy is so big that I think the likelihood that we'll ever know about any other intelligent life is almost zero. Not quite zero, but almost zero. That means it's worth listening, and one day we might discover it, but we shouldn't be depressed if we don't. It doesn't mean it's not out there. It means we should keep searching. And that's what makes life worth living, it seems to me, the searching rather than the finding. And so every day we should keep on searching both for the universe and life, and searching in our own selves for how to make the world a better place. So maybe that's how I'll end
Yeah.
my talk.
Okay.
So we need to finish now, and I need to say this is not a lecture for me; it was a classroom for me because I learned a lot with you.
Well, thank you. Well, thank you. I hope the rest of the people enjoyed it and learned something, and it was a pleasure to be with you, and a joy to be with you. And I hope I can get to Brazil in real sometime in the near future. Thank you very much.
Yeah.
Take care. Bye-bye.
Thank you, Professor. Bye-bye.
Thank you so much.
Good night.
Bye-bye.
Então, pessoal, foi essa a nossa palestra com o professor Lawrence Krauss, a professora Glaucia fazendo as nossas perguntas ao nosso palestrante internacional. Amanhã teremos a palestra com a professora Jill Tarter, no mesmo esquema. A professora Glaucia estará aqui com a gente para poder fazer essa tradução das perguntas, para quem tiver dúvida em como desenvolver a sua pergunta, o seu comentário em inglês. Começa também no mesmo horário, a partir de 6h30. Esperamos que amanhã não aconteça nenhum imprevisto. Né? O primeiro dia que era para ter acontecido a palestra dela acabou tendo um hackeamento da conta dela, por isso ela não conseguiu participar, mas amanhã a gente já confirmou com ela, já consegui conversar com ela, vai ter a palestra da fundadora do programa 7, que é o programa de busca por vida inteligente fora da Terra. Então, eu vou colocar aqui mais uma vez, para quem quiser aprender a falar inglês tão bem quanto a Glaucia, muito melhor do que eu, aqui está o contato dela, vocês podem mandar e-mail para ela para saber como é que é para fazer contato em relação a, durante a pandemia e pós-pandemia também, as aulas, os preços, os dias, horários, vocês podem contactar ela através desse e-mail que eu estou colocando aqui para vocês. Então, pessoal, a gente vai para a próxima palestra que vai acontecer. Eu vou colocar aqui no chat para vocês o local. Aqueles que já tiveram já podem se encaminhar para lá. Aqui no chat estou colocando o endereço da próxima palestra. Vai ser com o professor Alan Alves Brito, da Universidade Federal do Rio Grande do Sul. E eu espero que vocês tenham gostado dessa palestra, que continue não só na próxima, mas durante todo o evento. Glaucia, mais uma vez, obrigado pela sua participação. Eu
que agradeço, Bruno, pela oportunidade de conversar com o professor Krauss também. Foi fantástica a palestra.
Muito obrigado. Bom. E a gente se vê então amanhã, Glaucia.
Então, até amanhã.
Abraço,
até mais,
tchau, tchau, pessoal.
Tchau, tchau.
A gente se vê lá na próxima palestra, pessoal.